Looking at para versus diamagnetic materials, we know that something that is paramagnetic, a paramagnetic ion, is actually attracted to a magnetic field. And that's because in a paramagnetic material, we have electrons that are unpaired in their atomic orbitals. And so since we have one up but not one down, that net spin or movement isn't balanced out, and you have a paramagnetic system. It will be attracted to a magnet. Diamagnetic materials then will have all 100% one up, one down paired electrons. And in fact, they are very, very, very weakly repelled by a magnetic field. But that's an effect that you would have to have extremely sophisticated measuring equipment to see. To our eyes, essentially, something that is diamagnetic will not be affected by a magnetic field. So what I've done is I've set up a little demonstration where we have several different salts, and we're going to see if they are attracted to a magnet or not. Looking at what salts we're going to be using. Most of our salts, if I had it available, I used the sulfate salts just to minimize the variables. But if we think about it, why would an anion always be diamagnetic? You're right. When we make an anion, we're adding electrons to fill those empty spots in orbitals. So in an anion, all of the electrons should have a pair, and it would be diamagnetic. So I'm going to give you 3 minutes to write the electron configurations of the element and then the cation in question. So since 2 of these are iron, you only have to write the iron element electron configuration once, but the cations will be different because one loses 2 electrons and one loses 3. Now remember, you are always going to lose electrons from the valence, the outermost largest number shell first. So you have to think about what that's going to mean for a transition metal. here you can check your electron configurations. For a transition metal, we're always going to lose the 4s electrons first. That is the valence farther out shell. And so now you can see the electron configurations for all of the cations would have no 4s electrons. And in the case of iron 3+, it not only has to take those two 4s electrons, but it also has to take one electron from the d orbital to take away 3 electrons. It's also a nice thing to note that in fact iron 3+ and manganese 2+ have exactly the same electron configuration as cations, where they certainly do not as elements. Also, please notice that you cannot just write argon for the configuration of calcium 2+. That would require you going down to neon as the shortcut and then putting in the 3s2, 3p6. You can't just put argon in a bracket. That's not going to be enough to get you points. Now that you have the configurations of the cations, it's time to make a prediction. So you're going to decide if the ion should have unpaired electrons, be paramagnetic and attracted to a magnet, or if it should have all paired electrons, be diamagnetic and therefore not be affected visibly by the magnet. So I'm going to give you 2 minutes to make your predictions. In this one, we have our iron 2 sulfate. You can see there are 2 ends to this, and it's moving very, very slightly just because I moved my camera here. But we want to see if it will respond to our magnet. And this is a nice strong neodymium magnet, so it should be able to generate a pretty good magnetic field. So now we'll put this over here. Oh, hello. Let's see if we can do that again. You can see it rotated back kind of where it was. And if I put the magnet close, I can actually pull this with the magnet. So this has the characteristic reddish color of iron oxide, iron 3 oxide, or rust. And so I'm going to come here with the magnet and bring it in close to this and see what, ooh, there we go. So this also appears to be attracted to my magnet. You can see I can pull it all around. In fact, if I let it get too close, it will actually stick itself to my magnet. There it goes. Our white powder here is the manganese sulfate. And we're going to bring the magnet in close to the manganese sulfate. Oh, and there you can see again that this one is attractive to the magnet. I can actually even pull it and rotate it a little bit because it is attracted to the magnet. It does respond to the magnetic field. In fact, it actually sticks itself to the magnet. So this is fairly strongly paramagnetic. So this is kind of a bright blue-green like many nickel salts. And we can put the magnet near it and see if we can attract this to the magnet or not. Oh, 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 oh. It's not as much of an effect, but it does definitely seem to have some effect. You can see it starts to pull towards the magnet. So let's try the calcium sulfate and see if the calcium sulfate will show a pull towards the magnet. It seems to be moving just a little bit because of my air conditioning, but it definitely doesn't seem to be attracted to the magnet consistently in any case. So even if I get the magnet really close, it really doesn't seem to do anything other than just move back and forth a little bit in the breeze. And this is the last one, our zinc sulfate, that we're going to try and see if we can attract to the magnet. So I'll get in here with my magnet and we'll see if we can get a consistent pull towards the magnet. Keeping in mind that we do get a little bit of back and forth just from the wind blowing from the air conditioner, but I don't see any consistent pull. So here are our results for our test salts. We found both of the iron and the manganese salts were strongly paramagnetic, that the nickel salt was paramagnetic, but maybe only weakly. It wasn't as strong of an effect as we saw before. And both the calcium and the zinc were diamagnetic. They did not appear to be attracted to the magnet. If we look at the orbital diagram of the 5 degenerate 3D orbitals, because remember, all of these as cations would have empty 4s orbitals. Then if we remember Hund's rule, which says that you half fill a set of degenerate orbitals before you go back and pair, you can see why the iron and the manganese salts were very strongly paramagnetic, because they either have 4 or 5 unpaired electrons. The nickel, when we notice it has 3d8, so you would have 5 electrons and then go back and pair up 3 of them. So there's only 2 unpaired electrons there, which explains the weak paramagnetism we see with the nickel salt. Calcium and zinc, on the other hand, calcium is a main group element, and so it has a configuration identical to a noble gas, which means everything is paired. And in zinc, we have a complete paired set of d orbitals. So there's nothing unpaired there, and those are diamagnetic salts. So you can see, even though this seems to be something kind of esoteric and strange and just about little tiny electrons, those little tiny electrons being unpaired does cause a difference in the actual physical properties of those salts.